Thank you very much, Jose. Thank you for staying. I know there's a conference waiting for us, so I'll try to be fast and give all the information you might want to see. So that was my Christmas gift. I got that, gray boy around Christmas. I had 6 months where I had to bite my tongue not to disclose everything. So today I can finally share all of that. So I'm really excited. I have to thank Jose, Jason, who did a fantastic work in supporting us, Vince, who's the guy that is in front row that actually ran more than 5,000 samples on that instrument. So it was really a stress test, and I have to say it's been a lot of fun. And for the things I'm going to show you today, it's Adriana. And there's big teams behind that, but those were really the main actors. So thanks to all. I recently sort of wrote, I was actually sort of clearing my mind on what we need in metabolomics. And I think the beauty of that instrument, 8600, that really breaks, that frontier we have right now. Because as I'm hopefully going to show you is that it really allows you to see more and to identify more. So we're not limited by speed. Already the 7600 was really good by it, but we are mostly limited by what we can see, which is basically sensitivity, and what we can annotate. And I'm not going to show too much about this, but this basically goes back to the fact that we have different modalities. We can do also EAD. And that really extends, basically, the capacity to describe molecules that by CAD are not fully discriminable. So, I don't want to bother with the details. I mean, you hear 10-fold increase. If you ask me, I'm not SciEx, I would say it's more than this. I mean, they tend to be conservative. For me, it's 30. And, depending how you measure increased sensitivity, but it's clearly more than 10. The source, it's twofold. All of the optics is fantastic. The secret sauce in the isolated detector. And it's hard for me to show this, but I give you a sense, if you run a sample, this is now a lipid mix, so a bit of brain extracts, blood, plasma, everything you can buy from Avanti, you mix it and inject over 2 minutes. And what we're plotting here is basically sort of all the centroided data. And you literally can cover the entire range. In this case, it really goes to from a few counts up to 10 millions. And what's important that I cannot show here is if you start zooming in, and you start really zooming in a very crowded region, and you zoom in and you see these are all the centroids, you end up looking at a spectrum that looks so clean that it's fantastic to be picked. So there's no jitter, so there's no noise. We don't have any ringing. That it's very typical to be seen in time-of-flight instruments. There's no baseline shift if you have a very strong peak. And again, you might have a peak which is 1,000 times larger than some of the others, and we really have this purity of the spectra, which allows us, when we do the peak in the feature detection, to really discern nicely what is noise, and could be a few counts, and the noise is there, but what is really a real feature or not. So the beauty of it is across the entire dynamic range. It's really very nice quality in the spectra that allows us to be very aggressive in the peak picking, so it's really actionable dynamic range. And I'm happy to show this in real time and zoom into the data and so on. It cannot be done on a slide, but I think this is a bit of the secret sauce why this is, in practice, working so nicely. Okay, let's ask the real important questions. I'm not a big fan of specs, but what's the impact on, what's the value of this? Do we actually see more? I'm going to show you a lot of lipids, because for lipids we have a good sense on how the fragments, can you annotate them and so on, and it's easy to find, a sample which is very complex. Also, chromatography is not a major issue. I will show you some of the polar stuff at the end. Compared to the 7600, 8600, we typically see 3 times more feature. So we have 10, according to Nicola, 30 times more sensitivity. That really translates in seeing more features. And this is a number that is not so relevant, %. But what you see is that if you then look at how many of those features were picked by instrument in DDA, we frequently get, in this case, something twofold more precursors not identified, but fragmented. And if you then go with that data into a library search, in this case, we get roughly 40 to 50% more IDs. So we have more sensitivity that really translates in seeing basically the same things. What is important to notice is the following, is that if you now look at how good the matching was across the entire data set, there is no difference between maybe the 7600, that was actually a good instrument. We're still running this routinely for all of the routine large cohorts, and 86. We have the same average matching quality. In terms of purity of spectra, we have ways of measuring that. We also see the same. If you ask how many of the fragments of the library can be matched, it's basically identical. And for how many of these lipids we actually get also the neutral losses that point to the acyl chain's length and so on. It's identical. Basically, we see more of the less abundant guys with pretty much identical features as before, which is actually fantastic to have because it gives us, with the same confidence now, much broader view. We were not happy with this. Oh, this is how it looks. 15 minutes. It's left. It's 86. This is the 76. Any class you look at, you will see that you start spotting more features. And again, this is still a log plot. You can also make it more sensitive, so start picking other things. But in general, it's really, we see exactly in the data why this is doing a much better job. So this is 15 minutes. So we said, OK, let's really challenge. So that's probably the coolest slide I have, although it's very busy. So first of all, we did down to 2 minutes gradients. 2.2. It's ironical that the team was showing the same for peptides. So we didn't really talk before that. But that's how gradient you have to do it fast. So it's not rocket science. It's just a fast gradient with a short column. So, and then what you've done, you're taking dilution series. So the same samples we had, we did a dilution series. And every step is a 10-fold dilution. So from the left to the right, it's 1 million dilutions. And eventually, it's clear we don't see anything. But I think you can appreciate that in terms of number of features, which is not the major thing, how many are actually picked by the DDA in terms of MS2, and how many you can annotate. The 86 gives us everywhere much better reading. So if you have a diluted sample where you really care about sensitivity, we see really this huge gap where the 86 is able to find those features, fragment them, and we end up having 2 to 3 times more identifications based on MS2 searches. As before, you can dilute the samples 1,000 times, 10,000 times. You don't really see a drop in the quality of those matches. So you get the same quality, but you see much more, which, if you ask me, is actually a pretty nice result. And this is only 2-minute gradients. We see more. I'll show you this also for polar things at the end. The question is, can you do something else that was not possible before? One of the things is, it's really we can now do EAD that was introduced by Tim in a much simpler way. One of the problems of EAD, or the limitations, is that for singly charged species, as we deal with, it's not so fast. You get your molecular eigenes is always rather present. So there's a lot of seminal work. This is one of the probably more landmark papers on this, where they're showing that with EAD you get the fragmentation of the acyl chain. But these data is typically acquired very long. So for us was the question: can we now do this much faster, potentially even to be used in a complex samples, DDA, and so on? To do that, we needed a way to automatically assess whether a spectrum gives us the right annotation. So we have a little oracle. It's a piece of software that basically what it does, it takes the spectrum, it needs to know how many double bonds are there, what is the lipids, and then it generates the entire zoo of isomers. And for the entire zoo of isomers, it's going to generate the spectra and then see what is matching. If you have 1 double bond, it's easy. If you have 4 double bonds, and these are your spectrum, measured in LC. So it's not direct infusion, it's LC. This case, it's something I think we had in the preprint now. We have 4 double bonds acquired for 120 milliseconds, and now just zooming in this part where the losses on the chains are. And again, we have 2 chains, so partially overlapping and so on. And that's more difficult. And the oracle basically checks, in this case, we have 1,265 isomers. For all of them, we check what the spectrum is in matches. And in this case, it will say, oh, it can be, I'm not sure, it can be one of those 3. But basically, we count how frequently then is the spectrum giving us the right answer. So it's just introducing what we use. So what we have done is the following: comparing the 76 and the 8600 by decreasing the time by which you acquire. So we start with 500 milliseconds on the 76, and we went down to 30 milliseconds. We never went lower than this. And you see that if we start from the left, with 1 double bond, it's easy to get a single one. Eventually, if you start saying, from 60 to 30 milliseconds, you start seeing this decay, where the software is not so sure because there's not enough time or not sensitivity to actually get all of these fragments to make the call whether it's position 9, 10, or 8. That's where you have this lack of confidence. What we see on 86 is, on average, we can go down to 5 milliseconds with no double bond, or we can go down to 10 milliseconds. We can speed up everything by 3 to factor of 5. So there's a limit in how many double bonds you can annotate everything because it's a complex problem. But in terms of being able to run this, the sensitivity allows us to do these high inference much faster. So that basically allows us to do EAD on a time scale where we can do DDA with 10 to 50 milliseconds on fast gradients and get this sort of spectra for a large number of things without having to do MRM type of exercise or targeted where we have to scan for half a second. So this is something that with 8600 now we can do. This was already introduced. We can also do DIA with this scan. The problem of classical Zwolf for small molecules, particularly for lipids, is that we cannot use the same trick that proteomics is using, because typically the fragments that pop up, they tend to have the same mass. Think of phosphocholine. All of them are 184. If you use chromatographic correlations to filter those out, you have the problem that in the region where phosphocholines elute, that peaks never comes down. So we really have a low correlation. That's why that trick does not work for small molecules or lipids and so on, because it's those diagnostic fragments that we need to are sort of shared. So ZT scan DIA, it's something we tried a lot, and I'm just showing you the data. And it's really at the end it works with a combination of the fact that you have a xenotrap that really has almost this lossless, representation of fragments, so we don't really losing anything. The speed is very important, and the general sensitivity. The speed is important because that allows us to have smaller windows to isolate with. So since we cannot really resolve some of these compounds by the fragment, we have to use narrower isolation on Q1. So speed allows us to have these windows. That's a comparison. Lipid still, 15 minutes. DDA, top 10, 5 milliseconds. And you have more features to start with, but just to give you a sense, if you do this with DIA, we typically get 20 to 25 MS2 scans per second acquired. Doing ZT scan, in this case with a 6 Dalton, a speed of 1,000, this is not really a challenging setup, it's going sort of slow. We get 650 DDA-like type of fragmentation within a second. You basically have one detector. He has to do MS1 and MS2 back and forth, but it's basically fast enough to still give you every second 650 fragmentation. And full dynamic range of 6 logs, all the things you've seen before, without basically having to do anything. How does that translate? Well, for every single feature we detect, and there's a difference in number of features because we have more, on the DDA, more points, so then the peak picker will say there are more features. But important is for ZT scan, we actually get for every compound in there, we get a spectrum. If we annotate, we actually see, surprisingly, I have to say, we see actually more ID on ZT scan compared to DDA, 50% more. With the same quality, even though we start seeing more fragments and so on, what we see clearly is that we start getting some chimeric spectra because we have a window of 6 Dalton. So there is some leakage, basically, or crosstalk from different things. That's a natural consequence. But be able to do this, actually, it's already it's quite amazing. And in terms of, you can look at the map, you don't really get a lot of false positives. This purity here ends up being ambiguity in the notation. So it doesn't add false positive in the sense that now we have all of a sudden a triglyceride somewhere else where it shouldn't be. But it might be that for this guy, we have now different diagnostic fragments, so we're not sure exactly about the identities. I'll show you slightly better in the next slide. We were not happy with 15 minutes. We tried, let's go faster. So just playing with the instrument. So what we did now, we did the same sample of 2-minute gradients, doing DIA with ZT scan DIA. And now we sort of push, we are fragmenting everything in the window from 100 to 1,000. We have to use a larger window. So we expect to have more of this crosstalk. That's natural things. And the speed is 3,000 Dalton. Again, we get, doesn't matter, but you get something like 660 DDA type of events, not DDA, sorry, MS2 scan every second. It goes slightly up. And I have to say, the problem we have here is that going very fast, we start getting more of problems in terms of sporadic, erroneous fragmentation because we typically check retention time on the lipids so that it's coherent. We don't have these misannotations. But on the 2 minutes, it's just less precise. That's why we start having some of that. But overall, we roughly get, with 20 Dalton, with increase impurity if you want, but all of the other matchings are fine. We roughly get 1,000 IDs, which is something which is quite gorgeous. And you can see the data. I will show the link at the end, so I think it's actually quite marvelous. What is the consequence of having different windows? So that's an example. I just basically took a slice. One of the biggest peaks is the TG546, the ammoniated. And now, depending what the window is, it's sliding, right? You might start seeing when you target this, having all the precursors making into basically the same bin. So the fact is shown here. We have 3 windows, 20, 10, and 6. And you see that with 6 and 10, so the precursor is somewhere here. It's removed. We always remove precursor window the matching. This is a real fragment. And then we start seeing with 20, a fragment that belongs to that guy that is on the left. So depending on the window, we start seeing more things. That's why we have this drop in impurity. So this guy is the guy that contributes in having a drop in purity, but we still have the correct mass of precursor. We still know how many double bonds and so on it is. So it doesn't really affect, in our experience, the call on whether, basically it doesn't screw up totally the annotation. We are doing a lot of research. We are not yet where we have solved everything, because clearly there's much I can do now in terms of how to purify those spectra. Something that works very nicely out of the box is just to do the isotoping. So if you do the isotoping, we remove a lot of these additional peaks and we increase purity. And this is one effect. There's something else we are actively exploring, is to which extent we can use this triangular shape that we have in Q1 to also do additional filtering. We are working on this. We just couldn't do everything by SMS. Maybe by MetSoc in 3 weeks we will get there. What doesn't work, and this is what expected, is that if you filter by the EIC correlation, it gets worse. And that's because of what I showed you before. Now 184, it's going up and never coming down. So any filtering based on chromatographic shape for lipids, for instance, it's inefficient. Actually remove the most important fragment. That's why we have to go different ways. But overall, it's very robust, and you have this chimericity that you have to deal with, but it's not blowing out the number of things you see. It's just potentially giving you some more ambiguity on the notation. That's something you can track. I just have 2 slides to show that everything I said somehow translates to other things. So we have been injecting everything from milk, gut extracts, serum, and so on. I'll show something for plants. I thought this is exotic, something where it's very complex. That's what we see on the tick, the same extract. This is a 3.5-minute gradient. It's a mixed mode gradient, so also very fast. So the tick goes up by 10 to 15-fold. It doesn't really matter. We pick more MS2 features. I don't have the time to go into that, but we take all of the MS2 and we go to tools like Sirius. So we use lipids because it's simpler to sort of annotate this. For these type of compounds, it's much more difficult. But if you start using tools like Sirius, where it's going to take the MS2 spectrum and it's going to build up the entire tree of fragmentation to identify the molecular formula, a lot of those peaks, it basically can be matched. So it typically get those spectra flag that's high quality by Sirius. So basically, we really get much more high quality spectra with the new instrument compared to the old one. If you now try to annotate, there's so much behind it. So we have spectral searches, but then we have all the fingerprinting coming from CSI Finger ID. We have taxonomy. Everything flows together. And for these compounds you have in this plant, we might not have the perfect compound in the library. That's why it's so much more challenging than things. But what we get is, also in this case, if you compare DDA on the 8600 compared to the previous generation, we get 2-fold more IDs across all of the classes. And some of them will be wrong and so on, but it's exactly the same parameters, type of settings, we really see sort of 2-fold increase. If you go to ZT-scan DAA with 20, and there's sometimes ambiguity, but again, we get this additional increase. So it's pretty much the same we see with lipids, and we have seen this in every different type of samples and so on, so this is throughout. This brings me to the end, and it's sort of busy for our concluding slides, but yeah, there's so much. So, that instrument has so much more horsepower in the engine. It's really crude, pure sensitivity. And the beauty of that, you can sort of use that to either go fast or deeper and so on. It's really something you can action. So we see typically 2 to 3-fold more features detected just in MS1 retention time space over 6 logs. This is actually fantastic. We typically see 50 to 100% more IDs compared to the previous generation. And if you start, looking at the EIA, we actually see more potentially annotated features. Again, this is ambiguity of chimeric spectra that we might try to solve in the future. But this is, really expanding the space of chemistry and biology we can explore. It allows you for the first time to do narrow Q1 type of experiment in the EIA in a sub-second timescale. And I'll show you a lot of that. Going to 2 minutes gradients, you can still do that. It's actually quite fun to work with it. There is some limits, but at the end, it's really about fitting this to the right type of study and expectation. EAD chromatography timescale for fast gradients. I think lipids is also not the best example for that. All the compounds faster, but even in that case, we get down to 10, 50 milliseconds. The beauty of this instrument, it allows you to do so many things. At the end, you have to decide. There are some cases where you imagine doing more DIA, some other way to do more DDA. It really depends on the type of study. But you can pretty much do anything here at virtually any throughput, which is the beauty of that. We sometimes go to 2 minutes if you have 2,000 samples. If we just have a dozen, we stick to 15 minutes. You will get better data, but the beauty of that, it's really flexible. And what is important is it works now. We are in the lab for 6 months. We never clean it. So we never had any service. We injected all type of dirty samples, right? I think we changed so many columns, but the mass spec is still, perfect shape and so on. And in that sense, I think it's really something that, for now in the lab, it's now the most wanted piece of hardware where everyone wants to go because it's really the one delivers. There's a poster by Vince where we're going to also present the data. All of what I'm showing for the lipids, not for the plants because I've been too much. It's available online. Please come to me, ask. If you want to run samples, come to Zurich. I'm happy to discuss whatever. So thank you for your attention, and I'm happy to take any questions.